Right. So this is work that was done together with Irvin, Wu, and Giancarlo Di Giuseppe, as well as people from the Dart group, on basically trying to. Oh, I think I missed you. Yeah. Sorry, something happened. Yeah, here you go. To improve individual level state transition model speed by mostly using GPU, but also moving into different types of languages. So um, large models sometimes require large synthetic populations or long time horizons and repeated PSAs that all these, as we know, increase the computational demands. And you can build a discrete event simulation, you can build a discrete time simulation model. And we're going to focus on discrete time simulation models in scenarios where you have frequent events or frequent changes in dynamic characteristics, or you have multiple events that you want to track. And also because they are quite similar to cohort models, and sometimes users that they begin to use in the individual simulation models might have an easier time understanding them. So that creates all this complexity of individual level, cycle level, and PSA level iteration. And back in 2018, we put out a paper on how you can build that basic microsimulation models in R. And basically, together with Dart, and this is an effort to basically improve on the computational speed that that original microsimulation tutorial suggested. So one thing to understand as we go through it is this interaction between high level and low level languages and machine code. We're trying to minimize that kind of back and forth between high level and machine code language. And that is going to be one of our efforts, and how we have been doing that in the past has been so by avoiding loops as much as we can, because we know that their implementation is rather slow, usually in an R environment, and try to vectorize as much as we can, which allows for faster matrix level operations, less back and forth between R and low level language. They can be memory intensive. Another approach that has been also tried is parallel processing, of course, with packages like Future or Parallel, which nowadays with multiple CPU cores that reduces the efficiency. But again, you have memory constraints sometimes. And you can also use lower level languages, and that will result in faster operations, but that creates a barrier for new users because you are now introducing a harder language to learn. So we moved from the multiple loops to the vectorization approach, and from there to parallel processing. And what we are proposing essentially is that in addition to all that, you can consider incorporating GPU processing. We haven't seen it happening in HTA. Maybe we haven't looked enough, but the advantage is that you can have thousands of parallel cores that they can execute either on an individual or a PSA level, as we will discuss. And modern GPUs, they have thousands of cores, and they have been popularized through the use in AI and big data. A lot of the methods that we have at HTA are parallelizable. You have PSA, individual model, like individuals, and as well as like Bayesian calibration, or Bayesian calibration is also something that can be incorporated into the GPU approach. And that allows you for larger populations, more PSA iterations, more scenario analysis, and or perhaps faster development and validation. The good thing is that GPUs are kind of available and accessible to the only problem is that as it was discussed yesterday as well, they have become ridiculously expensive. So the objective of today is to develop a GPU-enabled implementation of an individual level state transition model, demonstrate how these GPUs can reduce computational runtime, and compare across vectorized solutions, parallelized solutions, and traditional kind of for loop solutions. We also implement this in both R and Python to understand relative advantages, and Python with a spin, as I will discuss. and we quantify gains in computational efficiency and scalability. So this is a bit of a loaded graph, but we tested 6 different options. Basically, one is to do a plain vanilla triple loop of for every cycle, for every individual, for every PSA, run it through a triple for loop. So for every PSA, create an individual, for every individual, assess them at a given time cycle, move on to a different time cycle, move on to a different individual, move on to a different PSA, and repeat. You can do that with one core, you can do that with multiple cores in the CPU, and you can do that with multiple cores at the GPU level. Another option we have learned to use is vectorization, and I'm also forgot to say that all these reflect do it your own micro simulation as opposed to using a certain package for it, like Keymonde or Hissing. So you're building your own micro simulation in a vectorized form where you vectorize all individuals at a given point in time. So instead of looking at one individual at a time, you kind of pass through all individuals at time t, t+1, t+2, and so on. And then you maybe loop over PSAs. Oops, sorry. You can do that vectorization through parallel processing over PSA level. So across different PSAs, you send a different PSA at a different CPU, or you do the same with a GPU. You send a different PSA at a different GPU core if you want to. Now, GPUs have thousands of cores, so we tested to understand which one has a relative efficiency. We did some other things to improve speed. So we made sure that all elements in the code were of numeric form when possible and declared and optimized their size and type. Whenever possible, when people entered the death state, were removed from the model. This is not possible always in a vectorized approach. We tried to improve memory management. So we released large matrices as soon as they were no longer needed. And we minimized computational expensive operations such as searching or matching and repeated conditional evaluations of large matrices. We tried to avoid using if-else statements as much as possible and use conditional statements instead. And sorry, there's a lot of noise in the background. I'm really sorry. And then we pre-extracted model parameters outside of the loops to avoid repeated conditional evaluations during simulation. We tested that into a simulation setting where we built basically a 3-state model with 2 strategies, monthly cycles, baseline characteristics on sex and age. We used stochastic rates on cost and utilities, and we varied the population size and the PSAs that we would run. We measured incremental cost and qualities, we standardized the seeds, and we repeated 20 times across seeds for stability, simple 3-state model. And we evaluated all algorithms across multiple population sizes and PSAs, as I mentioned. We looked at computational runtime in seconds as the primary outcome. And we wanted to compare against the vectorized CPU implementation, which is the kind of proposed in this 2018 paper, proposed the fast implementation. We assessed convergence using a Monte Carlo error, and we compared stability on incremental cost and effect. We used R with the package Torch that allows you to run GPU processing in NVIDIA cards. And we use Future for CPU parallelization. And in Python, we used NumPy, but also Numba, Numba is basically a trick to get Python code converted into a lower level language and compile it and execute it through Python. So we access it through Python, we compile it, and we run it through using Numba. We used a strong computer with 16 cores, 256 gigabytes of RAM, and 16 gigabytes of VRAM for our GPU. The code, there's a GitHub repository which is currently not public, but it will be. The paper is under submission now, and because of that, there are some things that we need to address. But you can keep note of the of the GitHub, and it's going to be available in the near future. Quickly going through some of the results. Basically, the first slide, sorry for the small font. We tested whether the costs and quality estimates were similar between the different methods. So just to validate that we are not calculating something strange out of one of these methods, and all of them converts to the same roughly values. We standardize the seeds as much as possible to avoid having any seed-related variation. Here's the main theme, or the main interesting result. Basically, on the left-hand side, you have Python. On the right-hand side, you have R. You can see that if you use Python and you use the trick to convert Python with number, your implementation is going to be much faster. So it took about 9 seconds to run 1,000 PSAs with 100,000 individuals with a number conversion in the GPU. And you can see it's in the logarithmic scale time, and you can see how, starting from the top, where you have a vectorized CPU approach and going down through a vectorized and parallelized, or a simply parallelized approach at Python, and then further lower using a PyTorch GPU, which is like using the GPU directly from within Python. And then further at the bottom, the much faster approach is using the GPU by converting first using number into a lower level language. So basically, you're sending all the information, including the input, to the GPU and letting the GPU do the work using low level language, as opposed to back and forth between Python, GPU, and back. On the right hand side, you have the R results. The triple for loop was the slowest by far. And you can see again that vectorizing improved, parallelizing over PSAs improved further. Vectorizing and parallelized was the most efficient non-GPU approach that we used. And then if we were to use Torch, you can see some relative gains after, once your problem became quite complicated. So at 1,000 iterations and 100,000 individuals. It's only there that we saw GPU really doing better in an R environment. We also looked at convergence just to make sure that, different seeds do not correspond to different speed of convergence across the different algorithms. And you can see as we increase the number of individuals, convergence is achieved as expected in both Python and R. So briefly, GPU computing matters for decision models for HTA purposes. You can achieve up to 2,500 times faster implementation of this simple 3-state model with a GPU implementation in Python than conventional implementations. But even within an R environment, this improved about 80 times or so compared to how we would do parallel processing or a vectorized approach in one CPU. So parallelization and GPU useful, especially in Python, but also in R with complicated problems. You can do that using a consumer grade level GPU. You can also do that, of course, using server-based GPUs. Compute Canada, for example, in Canada offers this option to use their GPUs, but it requires the ability to use these GPU kernels and the knowledge of using either Numba or Torch, which Torch requires tensor-based programming. So that means that there's complexity in the way that you actually code your model. To some degree, you have to learn to code in a way that your GPU will understand. And you have to understand what is, as with a lot of different things in computer programming, you have to understand what makes your GPU use efficiently the architecture and its memory. Data transfer between CPU and GPU can offset gains for small models, so you have to really know when you're going to use it. GPU memory is more limited than RAM. So in most of the times, if unless you can really afford it, so that limits the amount of things you can send to the GPU in some way. And you might have to introduce patches in your iterative processes. As I mentioned, greater program complexity and learning curve. And with this method, we got a good understanding of how GPU methods can be used in decision modeling in R, but we don't have uh, an understanding of how these methods are going to be able to be scaled to higher order models with more health states and more interactions between these health states. So that is our next step to implement into a more of a real life example to be able to understand better the limitations of the GPU use. So thank you very much. Again, sorry for the background noise, and look, happy to answer questions.
Many thanks, Petros. I think the background noise wasn't that bad, so don't worry. I think it was very good. Any questions from Petros? Nothing. Well, I might kick things off. It was striking that graph that you showed with the gains in terms of performance. So that those are striking. I mean, and particularly for the GPU enabled implementations. So I guess that you can think of um, areas where you can gain in even further. So doing larger PSAs or considering a lot more else states if that's the case, or even more reflecting more complex patient pathways. So what sort of complexity do you think it will these particular implementations can benefit more?
Yeah, I think a lot of the times when we are, a lot of times when we are moving away from a micro simulation model because of the fear of the potential um, real world inability to execute number of scenarios for enough PSA iterations and for enough individuals, for example, in screening models or where you need a large population to screen so you can detect a change in your intervention, uh, or in models where we shy away from incorporating uncertainty appropriately because we lack the computational capacity, um, better scenario analysis. Sometimes you don't do a scenario because it might take 7 hours for it to run, and you're limited in time. So in all these examples, then these examples will be hopefully will benefit a lot from a GPU implementation. I have to say, knowing that this is an R-HTA conference and me being very much invested or interested, involved in the R component of decision modeling, this Number implementation of Python has been fantastic. So, especially if you're in need of something fast, it's not very complicated. It's almost easier to implement that than implement a version of GPU implementation in R. So I would suggest people that also have a look at it. It's
Yeah. I was actually going to ask you that, Petros, because I mean that maybe we need a Python HTA as well group and workshop.
I
Um,
think I
but
think
yeah,
we should be using whatever language for whatever purpose optimally. That's all.
yeah.
And for,
But where do you think the balance lies between staying within the
yeah,
R ecosystem or adopting, like you were saying, a more of a Python-based workflow? Because I mean, obviously, as you were pointing out, Python does better, but I'm sure there is a balance.
yeah. Um, I would say maybe the golden middle is at least the optimal use of your memory capacity and knowing, defining the ranges of your matrices vectors, the types of your matrix vectors, and then implementing a CPU parallelization That is the largest gain for the smallest investment, in my opinion, with regards to learning a new language or modifying the existing. If you have an existing model that is slow, that would be the first thing I would do in order to improve parallel processing and improving the uh, the underlying kind of architecture of your own code.
Very good. Thank you for that, Petros.